Hey guys, for this lesson we're going to look at graphing motion, mainly representing motion as graphs. We're going to look at displacement versus time graphs, velocity versus time graphs, and at the end we're going to look at some example questions. So let's get into it. First, we've got this displacement versus time graph. Now a few things we need to note with this. Displacement on the vertical axis, time on the horizontal axis. I guess the only thing we need to look at is what does the slope of this graph mean? Now, we know from maths in school that the slope of the graph, or the gradient, is the rate of change of the y-axis when t is on the bottom. So, what is the rate of change of displacement? It's velocity, isn't it? Remember that from previous videos. Cool. Other things you got to note is above the 0 point displacement is positive, below is negative. I guess that's pretty self-explanatory. So let's move on to the velocity versus time graph. Here we've got a velocity versus time graph. Pretty similar, only velocity's on the y-axis this time. Here again, if we look at the slope of the velocity time graph, what do we know about the rate of change in velocity? It's actually acceleration. So the slope of this graph is actually the acceleration of the body. Now we can see here the slope is negligible, or zero here, which means that the velocity is actually constant. So this line here represents a constant velocity, which means no acceleration, which makes sense because the velocity is not actually changing. So that's the velocity versus time graph. One quick thing, the greater the slope, so we can see here it's relatively gradual when you compare it with the slope of the graph over here. So the greater the slope, the greater the acceleration. Just like with the displacement versus time graph, the greater the slope, the greater the velocity. So that is something we can use to compare different graphs in the following examples. So let's look at some examples. So I've drawn an example over here. Right, we've got a few different lines. We've got a displacement versus time graph, and we've got a few different lines, and we've got a few different questions concerning the lines. So, first question, which object or objects have a constant velocity? Now, that means that the velocity doesn't change, so that means that the slope of the line doesn't change, because the slope of the line is the velocity in a displacement versus time graph. So the slope of the line doesn't change in A, doesn't change in B, doesn't change in D, and doesn't change in E. So let's write those in: A, B, D, and E. Cool. Which ones are accelerating? That means the slope of the line does change. So it's just the opposite of the first question. And the only one we didn't put in was C. So we can see that the rate of change of displacement is actually increasing as we move along T. So that one is accelerating, so we'll put C there. Which one changes direction? Now, we said before that below the x-axis, or below the 0 point, is negative, and above the 0 point is positive. So we can see here, this one is moving towards the 0 point and then past the 0 point. So that one doesn't change direction. This one's moving towards the 0 point and then past the 0 point. So this one doesn't change direction. In fact, none of them change direction based on those that understanding. So here and A, none of them change direction. Which ones don't move? So that's the one with constant displacement. So that'll be no change in this. These two flat lines over here, both of them don't change in displacement. So we've got A and E. Which one travels the fastest? Well, that's the one with the greatest slope, and that's clearly B, because like we said before, the greater the slope, the greater the rate of change in displacement, and that's the greater the velocity. Right, I've got one more example that you're likely to see in examinations. Okay, so we've got quite a weird looking graph over here. Right, I'm just going to move that up. We've got quite a strange graph over here. It's a velocity versus time graph, and we've got a few questions. So, number one, can we find the acceleration between times 0 and 12. So let's see, the acceleration is actually the change in velocity over a certain time. So over 12 seconds, the velocity changes from 0 to 4, right? So if we just write that in down here, acceleration equals change in velocity over change in time, which equals, we said from 0 to 4, so the change in velocity, it changes 4 over time, 12 seconds. You'll find that is, I guess, 1/3 units per second squared. So the velocity is increasing at 1/3 units per second squared. The acceleration between time 10 and time 12, so we can see at time 10 it's 8. At time 10 the velocity is 8 and it moves down to 4 by 12. So that is exactly the same. It changes by 4, only this time it's negative. So we don't need to go through that whole process again. We can just write that the acceleration here is just the opposite, so minus 1/3 units per second squared. Right, the displacement between time 0 and 2. Now to find the displacement, like we effectively found the derivative of the graph of a displacement versus time graph to get a velocity versus time graph, to go from a velocity versus time to displacement versus time, we just integrate. So effectively it's the area under the graph. So to find the displacement between 0 and 2 seconds, we just need to integrate the area under the graph, or find the area under the graph. So here it's a triangle of base 2 and height 8, right? So base 2 and height 8. So to find the displacement for 3, it's just the area of that triangle. So half times base, which we said was 2, times height, which we said was 8, equals 8 units. So the displacement between 0 and 2 is 8 units. Now for the next question, we need to find the displacement between 0 and 8. Now it's always moving forward. The velocity is always constant. So while it looks like it's moving back towards the origin here, it's actually not. It's still moving away from its point of rest because the velocity is still positive. So if we look at how far it goes in 8 seconds, we end up with I guess a trapezium. Yeah, we've got to find the area under that graph. Now we've already got this area, that triangle over here. Now we just need to find the area of this rectangle. So if we look here, we've got a base length of 2 plus 4, that's 6, and we've got a height of 8. So for our displacement, equals the area of the triangle, which we worked out to be 8, plus the area of the rectangle, which is 6 times 8, which is, I guess, 48 plus 8, so that's 56 units. So it's actually moved 56 units away from the origin. Now that is a really important point, that even though this slope is going down, the body is still moving away from the graph, from the origin. Alright? And the last one, describe the object's entire motion. Now we're not going to write that, we're going to talk through that. What you'd say is possibly the origin, the body starts at rest because the velocity starts at 0. That's always a nice way to start. Velocity starts at 0 and accelerates to 8 units per second in 2 seconds. It then maintains a constant velocity for the next 10 seconds, or for the next 8 seconds, sorry. Then decelerates to 4 meters per second, 4 units per second over 2 seconds, and then maintains a constant velocity from 12 seconds to 16 seconds, and the constant velocity is 4 units per second. So a nice thing to do here would be to say what the final displacement is. I mean, you can go into a lot of detail. You can say what the acceleration of these points are. Basically, to describe the motion they want, what happens at the beginning, a brief overview of what happens in the middle, and where is it at the end. So effectively, that's what we just talked through. And that brings us to the end of this lesson. Thank you, guys.
Cut study time with concise video summaries by top students. Visit spoonfeedme.com to view more free videos in this course and hundreds of others.